Сейчас будет лет, да? Да, будет. Were you just using a blackboard?
Yeah.
Good.
That might be my marker. Yes, I'll change it. Yeah.
The CN tower, the big tower in Toronto. Me too, many times.
В архиве есть, конечно. В архиве они журналы переводят. Для подписчиков.
Значит, если вам не сложно, я лично чтобы вы не забыли, вам значит, бумажки с моей я не изменился, но у вас он есть, но это слишком
Sagrada Familia. Sagrada Familia.
What?
The highest cathedral in Barcelona.
It would be much lower. Yes, definitely.
У него там 4 еще и я эту фамилию. Столетние люди. Я пишу так. Из Японии просьба презентация моего доклада сделана 5 июня в Институте физики и математики Вселенной. Нет, я сказал, что картинки писать могу. У меня доклад был такой же, да. Картинки вот я те же самые тоже. Картинку могу прислать, пожалуйста. Взвешивайте. Презентации у меня нету.
There is an announcement from the organizing committee for people who enjoy coffee and who want to do it any time, not only coffee break.
What about need coffee?
Okay,
Not just
for
enjoy,
people,
need.
who need coffee, you can take it any time on the first floor of this building. There is cafeteria downstairs, so you can take it. It seems. I didn't try, but very much. So please enjoy if you need to use it. Okay, so it seems we can continue now, and our next speaker is Tom Glaze. My pleasure to introduce him. He's professor in Federal Institute of Technology. In this colloquium, he gave two lectures, and now this is the first part with a long title. So okay, you explain it. So please.
Yeah, thank you. First, I would like to thank the organizers for inviting me here. It's great to be here. So this is my first time to Magnitogorsk. I studied a long time ago in Moscow. Never visited Magnitogorsk before. Well, as I understand, Magnitogorsk used to be close to foreigners. Well, actually at that time, even just to get out of Moscow, I, as a foreigner, would need a visa. And I must admit that I broke the law several times, going out, visiting, well, seeing some secret outside Moscow. But I never actually dared to go as far to places as Magnitogorsk. That's my first one. Okay, so my talk is about, well, and also it seems that my talk, the this conference is about quantum topology, and it seems that my talk will be the first one on really on quantum topology. But actually, the first talk will be closer to number theory than to topology, because I would like to explain a very remarkable ring in quantum topology, and now it's also very well known in number theory, which is the Habiro ring. But first, let me give some overview and motivation for what I'm going to talk here. So I will give a brief overview and history of some invariants in quantum topology. The first one is the Jones polynomial. So I have here the Jones polynomial, which was discovered by von Jones in '84. So I write here as JL. Well, maybe it's just so it's just J from the set of all arithmetic links links I mean in S3 to the set of Laurent polynomial in some quantum variable q to the 1/2, and this is a link invariant satisfying the following scale relation. Which means the following. If you have three links which are identical everywhere except for a small one in which this is the first, this is the second, this is the third, then the Jones polynomial of these links will satisfy this identity here. So usually it's known as the scale relation. And the second one is if you have a trivial knot which is far away from a link L, then the value of this combination would be just, I will write here quantum 2 and then the value of L, where I use the standard notation for quantum n for any integer n will be q n half minus q minus n half over q half minus q minus 1/2. So quantum 2 will be just simply q 1/2 plus q minus 1/2. Okay, so, well, you can use this as the definition. It's very easy to prove that there exists. So uniqueness, uniqueness is easy. I mean, it's easy to show that if such an invariant exists, then it's unique. Okay, you can. Now, the existence, well, it's difficult to discover this, but once you discover this, it's not very difficult to prove existence.
Well, it's unique if you also require that the Jones invariant of the trivial knot is 1.
Right, yeah, so, thank you. So for normalization, I just put the value of the empty link. So I also consider the empty link as a link. Empty set is a link, and I require the value of this, the empty link. So the value of the unknown will be quantum 2. Okay, yeah, thank you. So this is the Jones polynomial, and Jones discovered this using, well, he first discovered a special representation of braid group in his study of subfactors. And then he used the so-called Markov theorem, which relates the arranged links to braids. And then soon after that, there are many generalizations. So there are many generalizations of the Jones polynomial. And the best framework for these new type of invariants is the ribbon category theory of Reshetikhin and Turaev. I will talk more about this in my second lecture. In my second talk, here I just mentioned, the final reasons is the following. Suppose G is a simple Lie algebra or a simple Lie algebra. Or again, I will just assume that just the K is not. So K is a not oriented. Okay, and well, so I will assume that it's a frame knot. So that's come with a normal vector field. Again, everything is defined up to isotopy, and V is a finite dimensional G model. Then you can define the Kerr-Jones polynomials J sub K of V, and that quantum perimeter, which is a Laurent polynomial in the quantum, well, a fractional power of the quantum of the quantum perimeter Q, where this number D here depends on the Lie algebra. While just you can take it to be 2 times the determinant of the quantum matrix of the Lie algebra. So the whole thing is defined through the quantum group associated to this G, to this Lie algebra G. In the simplest case, when G is SL2 and V is, so this is just the set of all 2 by 2 matrices, traceless 2 by 2 matrices. And for that you have the fundamental representation, which is just C2, well, 2 by 2 matrices naturally acts on C2, this way. Then this JKV here is exactly the Jones polynomial. It's the Jones polynomial. Okay. Now all these are defined using mainly diagrams, knot and links diagrams. So something 2-dimensional. So people are asking about something, well, relation to classical topology like the fundamental groups, or something more intrinsic 3-dimensional definition. And then Witten, I think it's in 1989, claimed that he has an intrinsic 3-dimensional definition of the Jones polynomial. He claimed it wrong. Say that if you have, well, you can define invariant of pairs.
I think it's actually 88.
Okay, yeah, maybe 88, but the paper is probably in 89.
Probably.
Well, the paper appeared in 89, so usually. Okay, so invariant of pairs, so you have a 3-manifold M and a framed oriented link in M. Then, well, and also a Lie group, but I will consider just a simple Lie algebra. Then you can define an invariant, which in the case when this M3 is S3, you recover the Jones polynomial. Okay, but again, only at Q is the root of unity. Only when Q is the root of unity. The definition of Witten is not a real definition because he used a path integral which is not mathematically rigorous. And then just a little bit time, well, later, so Reshetikhin and Turaev. So I think now it's 89, right? Right, it's in 89. Defined rigorously, well, so defined the invariant associated to the case when G is equal to SL2. So rigorously using quantum groups associated to SL2, define the realized well, we find Witten invariant in this case. And a bit later, with the help of works of algebraists like Henning Anderson, people, well, the work of Reshetikhin-Turaev can be extended to all simple Lie algebra. And so, at the end of the day, you have the following invariant. So if G, again, is a simple Lie algebra, M is a closed tree manifold. So I will flow oriented three-dimensional manifold. And psi is a root of unity, but some restriction on the order. So I write here psi is in Z sub G, where this script Z here is the set of complex roots of unity. So this is just simply the set of exponent of 2 pi I alpha, where alpha is in Q. So that's the set of all rational points on the unit circle. And this sub G here means that there are some restriction. There's some restrictions on the order of psi. And I will be more specific about this in the second talk, when I also, well, try to give the definition of this invariant, of this WRT invariant. That in this case, you can define an invariant is the Witten-Reshetikhin-Turaev invariant of the tree manifold M, which depends on the Lie algebra G and this complex number, a root of unities, which is a complex, just a complex. Okay. So, and then there are many questions. Well, certainly the most interesting questions are what are the relations to classical topology. Well, at that time, well, maybe I give you right away some examples so that you can see. So if M here is the Poincare sphere, sigma 2, 3, 5. So this is Poincare sphere. Then this Witten-Reshetikhin-Turaev invariant has M2 of, well, I write here to Q here, so Q must be a root of unity, and I write this the following form, so that will be 1 over 1 minus Q sum, and from 0 to infinity. So let me take here Q to the n, and here 1 minus Q2 n plus 1, 1 minus Q n plus 2, to 1 minus Q to 2n plus 1. Okay. The sum here is an infinite sum. However, when Q is a root of unity, whenever Q is a root of unity, this will become a terminating series. Okay, because this part here will become 0 when this number n here is bigger than the order of the root. This is this one here. This one here is equal to 0 if n is bigger than or equal to the order of the root Q. If Q is the root of unity and n is bigger than or equal to the order of the root, then this is just becomes 0 and the sum becomes a terminating sum. So it's just a finite sum. Okay. So you will see expressions like that. And okay, so this is a type of invariant that I will talk about. I mean the WRT invariant. And another type of invariant in quantum topology that is also the subject of tomorrow's talk is the Kashayev invariant. there's another type of invariance. So actually invariant of knot, Kashayev invariant, which is actually a specialization according to Murakami and Murakami's specialization of the Color-Jones polynomial. Kashayev invariant. Again, I will give the more precise definition tomorrow. Let me just give you an example here. So this is the graph one, and the Kashayev invariant of this will be. So I come here k sub k q. Okay, so this k is this dumb stupid knot here. Okay, and this k here is for Kashayev. So that's handsome gentleman over there. So please don't confuse these two k's. So that would be q sum, and from 0 to infinity. It's very simple here. You have 1 minus q squared up to 1 minus q to the n. So if you see, I mean, expression like this one, and again, I mean, this expression here will make sense whenever q is the root of unity. Okay, whenever q is the root of unity, again, I mean, this sum, this infinite series is a terminating series. It will become finite. So we want to understand what type of functions do we have here. I mean, we have the Kashayev functions. We can consider this as a set function from the set of roots of unity to C. Okay? And then we have the WRT invariant of three manifolds, which is also a function of roots of unity, maybe some restriction to C. And we want to understand functions, what type of functions do we have here. Okay. A long time ago, Kontsevich and also Lutz-Rollins made the conjecture that the WRT invariant, so this is Kontsevich and Lawrence, that the WRT invariant of M are always algebraic integers. Which, I mean, in the full generality is still open. And we want to understand also something like, although we have a function defined only at roots of unity, but we still want to make the expansion. So what does it mean? Q equal to e to the h. So u to the h is the Planck constant. In the knot case, the expansion of non-invariant, because non-invariant are Laurent polynomial in Q, so you can make this substitution, and then you have a perturbative invariant of knots in the work of Barnastan, Ling, Kontsevich, Berman, Ling, and so on. And we also want to understand the perturbative invariant using this expression here. But now, because the function can only be defined at root of unities, we need but still we want to understand this expansion. Okay? And it turns out that everything can be done through the so-called Habiro ring, which is I think it's a remarkable ring, not only in quantum topology, but also in mathematics. Well, actually, Yuri Manin told me that the Habiro ring will become something fundamental in mathematics. So now let me introduce the Habiro ring. We try to, and then next talk I will show that all these invariants here, the WRT invariant of integer homology tree space and also the Kashayev invariant of knots, they are all in the Habiro ring. Okay, so what is the Habiro ring? So suppose we have a ring between Z and R, so Z, so it's Q. Then we look at the ring of polynomial in one variable Q, and we make a completion, so head here, take the inverse limit of this Q over, so I will use here notation, standard notation in Q calculus, Q sub n, where Q sub n here is the problem 1 minus Q squared up to 1 minus Q to the n. So, and so
So it's not a usual completion, but a special completion.
this is the inverse limit.
I
so,
see, yes.
yeah, but some kind of completion.
Okay, yeah, I
Yeah,
see.
completion in very general sense. I mean,
Yes, okay. Usually one takes just the quotient over Q to the nth. Just a standard completion.
yeah,
But,
but-
here it's a special completion. I
yeah,
see.
yeah, some more complicated completion.
Yeah.
Okay, so Habiro ring is the ring just Z Q hat. Okay, so when this ring ground ring R here is the smallest one. So what is good with this ring? So it turns out that, so I want to argue that the Habiro ring is the ring of analytic functions on the set of roots of unity. And also, I mean, because of similarity between this ring and it has very nice properties similar to properties of analytic functions, and this is the reason why Manin called it the ring of regular functions on the non-existent field F1. Okay, so people are trying to find F1, the field with only one element. And Manin and Marconi will argue that this is the the ring of analytic function on F1. Okay, so first of all, so maybe so if F is in ZQ hat, I mean the Habiro ring, then F has a presentation of the form, so F will be sum n from 0 to infinity, F and Q and Qn. Okay, where F and Q here is a polynomial Q with integer coefficients. Okay. Any element here can be presented as an infinite sum like this. Okay, so this is easy from the definition. But let me give one example, which is I think very instructive example. Just to show that this presentation is not unique. Okay? So recall that this Q sub n. So let's look at the Q sub n plus 1. That is equal to 1 minus Q to the n plus 1 times Q sub n. Just by definition, because you just add the very last factor. And so you multiply this out, you get here Q sub n minus Q to the n plus 1 of Q sub n. Just multiply this out. And so I will just rewrite this identity. I have here Q to the n plus 1, and then Q sub n here is equal to Q sub n minus Q in brackets sub n plus 1. So it's just the same. And now I take the sum when n from 0 to infinity. Okay. Now what will be the right-hand side now? This telescoping series, you see that this one will cancel with the this term cancel with the next term, right? So eventually you get just Q sub 0. So it's just 1. Just 1. So it means that 1 is equal to this sum here. 1 is equal to this sum here. So you see that 1 has two different presentations, such a presentation here. And this one, well, something 1 is just equal to 1 is one presentation of this just Q sub 0, but I also have this presentation here. Okay. So in general, this presentation is not unique here, but it's easy to show that it's unique if you require the degree of this Fn here is less than or equal to n. Okay, so the general presentation is not unique, but it will be unique if you require the degree to be less than or equal to n. So you see that this is Q to the n plus 1, so this is the reason why it's not unique. Okay. But now we can, for example, multiply by the inverse of q. So I get here q to the inverse is equal to the sum, and from 0 to infinity, q to the n, q sub n. So in this case, fn here is q to the n. So what does it mean here? Because the q inverse relation is not in the ring. What it says is that q inverse exists as an element, well, the inverse of q exists in the Habiro ring. Okay, and it has this presentation here. And according to this presentation, it's unique. I mean, if you require the order of this, is less than or equal to 8. Okay, so in this ring, q inverse exists. Okay, but that is not. So this is just one simple example with elements. But well, actually, when I study quantum invariant and I arrive at this identity through the following geometric picture, I try to understand the invariant of this element. So this should be equal to this one here. Okay? If you understand if you know the theory of universal invariant, you put here the R matrix and so on, and then you calculate the invariant of the left-hand side and the right-hand side on the Weber model corresponding to minus rho, where rho is half of the sum of positive root. On the left-hand side, on one side you get 1, on the other side you get this sum here. So at that time I was surprised because why this one is equal to, should be equal to this one, and in what sense? And it turns out that they are the same in the Habiro ring. And this is a direct proof of this thing. Okay, so now what are the properties of elements of the Habiro ring? So let me list here a couple of properties, and you will see that they are more or less well, they are very similar to the class of analytic functions. So first of all, if you have an expression like this here, so it means that if f is in the Habiro ring, then f defines a function from the set root of unity to C. Because whenever I have psi here is a root of unity, then f of psi is equal to, we just replace q by psi here, so we have the sum, and from 0 to infinity, f of psi, and here it's just, so I have 1 minus psi times 1 minus psi squared, and so on up to 1 minus psi to the n. And again, if n is bigger than or equal to the order of psi, then this is 0. And so the sum is finite and have just a complex number. Well, actually, this is not only complex, but it's certainly algebraic. It's certainly in Z of psi. So, but the first thing is that every element of the Habiro ring can be considered as a function from the set of roots of unity to C. Okay? So that is the fact number 0. Now, fact number 1 is I want to argue that every such function is of class C infinity, and so you can associate a Taylor expansion, Taylor series to it. So you look at an expression like this here, and look at f prime, the derivative, just the formal derivative of this. So it will be, just take the formal derivative, you have the sum, and from 0 to infinity, and here I have so f prime n q times q sub n, plus f n q times, and now you take the derivative of this, so 1 minus q squared up to 1 minus q to the n prime here. Now, it's an easy exercise to show that this is actually divisible by exactly the same expression, but you just shorten this. So this is n minus 1 over 2, the floor, or the integer part of n minus 1 over 2. So you use the fact that the quantum binomial is a polynomial in Q. You can easily show that this one, the derivative is divisible by this one here. Okay, so it means that everything here you can. It means that the derivative here, this formal expression is also in Z in the Habiro ring. It's also in the Habiro ring. So it means that every element in the Habiro ring, the derivative is also in there. Okay, so you can take derivative, you can take derivative again, and so on. So every element in the Habiro ring is of class C infinity. means that f is in z hat, zq hat, then f is, you can differentiate f as many times as you want. And so we can define the Taylor expansion. So suppose you have a root of unity, you find the Taylor expansion of f to be, as usual, the sum and from 0 to infinity. So I take the nth derivative of f as psi over n factorial, and then this is q minus psi to the n. Okay, that's the derivative. So that belongs to, well, this coefficient here actually an easy, well, an exercise to show that, well, in general this is just complex number, but you can show that this is actually in z of psi. And so I get here the Roman polynomial z of psi, and then q minus psi. So a Taylor expansion at every element of the domain of the function. Okay? Okay, now let me formulate the theorem, which the main theorem of the Habiro ring theorem. Well, maybe I explain. Let's give so the Taylor expansion at what? So T1 of f is really simple. What is T1 of f? So let me write again. F here is I have the sum.
So what's the number of this property? So there was number 0, number 1.
I have not finished the number 1 yet. Okay. So f is n q, and then 1 minus q squared up to 1 minus q to the n. Now what I do is I just re-express everything in terms of as polynomials in 1 minus q. So this just rewrite this as polynomial in 1 minus q. So as polynomial in 1 minus q. Well, certainly, I mean, this division by 1 minus q is also division by 1 minus q, and so this is something in this part here will be in 1 minus q to the n times z of 1 minus q, right? Because this one here is given by 1 minus q. Yeah. So you just rewrite this as polynomials here, that this term is already in here, right? So it means that if we rewrite everything here, I will get a formal power series in 1 minus q. So the result is a Laurent polynomial. The result is in z of 1 minus q. Okay. Just rewrite each term as polynomials here. Then you get right away a formal power series in 1 minus q. And that is exactly the Taylor expansion at 1. That is exactly the Taylor expansion at 1. Okay, so now let me formulate the theorem here. This theorem was first proved by Habiro and also independently by Pierre Bourgel, some time ago. Is that, so suppose you have two functions f and g in the Habiro ring. Then at every point you have a Taylor series. Okay, now if you remember analytic function, an analytic function is totally determined by its Taylor expansion at just one point, and this is exactly the same. And if the Taylor expansion of f is equal to the Taylor expansion g at some point, at some sign in the domain, then f is equal to g. Then they are the same. Okay. So that is very similar to, so this is fact number 1. Okay. Very similar to the theory of analytic function. So what does this mean? That if I look at t psi, or maybe I just t sub 1, this is just the map from the set of Habiro ring. So from the Habiro ring to the set of formal power series in 1 minus q. Then the statement just says that this map here is actually an injection. Okay, this map is an injection. So the Habiro ring through this Taylor expansion is a subring of this ring formal power series here. And so in particular, So in particular, because this is a domain, this is also a domain. Okay, so usually if you define rings through inverse limits, it's difficult to prove that it's a domain. So in particular, this Habiro ring, ZQ here, is a domain. It's a domain. Okay. Now so actually this map here, this map is, the map T1 is injective, but not surjective. So this map is injective but not surjective. And it's actually very difficult to recover. I mean, if you know the Taylor expansion, it's pretty difficult to recover this one here. It's not easy. To contrast this with the case, now if I replace Z by Q, okay, so it means that in the definition, this F and Q here is in Z. So it means that F is now the sum F and Q, and then Q sub n, and then now this F and Q here is allowed to have rational coefficients. Then I can define everything like in this case here, but now the Taylor expansion map is quite opposite. So this Q hat here, and you map to the ring of Laurent of formal power series in 1 minus Q. And now this map, the second map here, when you replace the ground ring Z by this rational, is now will be, well, quite opposite. It's surjective but not injective. Okay, so you see that the fact that the ground ring Z is very important. Well, actually, the second fact is a lot easier to prove than the first fact here. Okay, it says that, well, in general, to recover, I mean, it's not, as I said, it's not difficult, it's not easy to recover the pre-image here. If you have something here, you see, if you have an algorithm to recover this one from this one, so can you apply that to a series when the coefficients are rational? Okay. So you see that they are quite, I mean, just quite very different here. And actually, this is the product of many rings containing the cyclotomic ring. Okay, so this is the fact number 1, and let me now explain fact number 2. So, an analytic function is totally determined by its Taylor expansion at just one point. Okay? And another property of analytic function is that if two analytic functions agree on a set having a limit point, then they are the same. Okay? So we have so this is fact number 2. This is also theorem of Habiro. Is that again F and G are elements of the Habiro ring. And again, this is Q, not Z. This is not Q. And suppose F of psi is equal to G of psi for every psi in a set. So this is a set Z prime, subset of. So Z here is a concept is set of all roots of unity, where this Z prime has a limit point, has a limit point. Then, so this is if, then F is equal to G. So this is
Limit point in C or just in Z? Limit point just any complex number?
yeah, limit point in Z.
Z.
Okay. But I have to warn you about the topology here. It's quite different. Okay. Okay. So limit in what topology? So, well, there are the natural topology is just the topology induced from
So this Z is such set of C.